And we use this function in order to find out. Okay, this is more natural because as the sender might not be waiting for the receiver all the time. Right? So this receiver is busy, very busy doing some certain things. Now the sender will not be able to process any further data. You have to wait. It means you have to wait for this receiver to complete. And by having this kind of situation, the sender actually is wasting time. While he has the processing power, but he cannot do anything because he has to wait until the receiver replies. Whereas asynchronous, which is more natural, you send the data, whether it's ready or not, you can proceed on to process other data. Okay? And once a while, you can go and check using this check receive or check send, find out whether the receiver complete. If you completed, then you send some more data. Okay? So it's more natural using asynchronous, but of course it's more difficult to program because you have to keep on coming back and check the data, check whether the receiver has already received it using one of these instructions. Okay, this one example. Maybe I should show you the synchronous one first, so that you have some idea. Okay, the sender calls send, foo is receiving the data, the receiver receive and input the data inside bar. Okay, so basically the message is sent over to the receiver. Then once the receiver receives it, it will send back the acknowledgement. So sender will not proceed until you receive the acknowledgement. So that is the synchronous. Okay, let's have a look at the asynchronous. The asynchronous also same thing, except that when you send, you use a different command. Actually, it shouldn't be send, it should be I send. The I in front indicates that there is asynchronous sending. Receive also same thing, there should be an I in front. Okay, that is to indicate asynchronous receive. Okay, the same thing, the data has been sent across. Look at the arrow, and from time to time, and of course you don't have to check immediately. You can do any other task, but from time to time you call check send in order to find out whether the receiver has received it. Okay, the same thing for the receiver. The receiver don't have to wait for the sender to send. Sometimes you have to wait for the sender to send to receive data. Asynchronous you have to do that. For synchronous you have to do that, but for asynchronous you don't have to do that. Meaning that if the sender is not ready to send, you don't have to wait forever. You can call this check receive to find out whether the sender has any data to send. If it doesn't have, then it will return immediately and it can process any other data. So the receiver don't have to check, don't have to wait for the sender to receive the data. What I mean is this. In this case here, suppose the receiver called the receive, right? But the sender does not send anything. The receiver will be locked. That means it will not return. The receive function will not return. That means the receiver will be locked. You will not be able to move on, right? Until the sender sends the data, then only you can proceed on to send the acknowledgement back. Okay, so that is not desirable. In this case here, no. In this case here, it does not call receive, you call this check receive first. Once it knows that there's a data, then only you call receive. Okay? And definitely receive will return. The reason is because the data is already there. When you check receive, it says that there's the data to receive. Then when you call the receive, you get the data straight away. Okay? So the whole idea of asynchronous is not waiting for anybody. Okay? This is the one that I was talking about, MPI send, MPI receive for the synchronous. So only two functions, very simple. But for asynchronous, you got three. Okay, you got MPI I send, MPI I receive, and MPI wait. So wait actually is used by both. Just now the example actually is for, not for MPI, it's just for general discussion. But for asynchronous, actually we use only MPI wait, whether for receive or for the send. Okay, you just wait. If let's say the sender want to find out the receiver already received, you just execute MPI way. Same thing for the receiver. Whenever he wants to find out whether the sender has the data to send on, you also use this MPI way. Okay, memory migration. This is something that we have done. I think some of you have already done this, already seen this slide. During the practical, I showed to you that the notebook that you open now, right? Those who haven't gone through the practical, maybe tomorrow you will experience it. But for most majority of you, have seen this memory migration happening, right? So what happened is, of course, you can also send data back and forth. Not only you can send data, actually you can send the process itself to be executed on another machine. You can send the code, send the data. Here, memory migration doesn't mean that you send only the data. You can send the whole memory, including the code, right? So memory migration requires two fundamental decisions. When is the process we want to migrate? Okay? When is it that we want to migrate? Second thing is how much memory that needs to be migrated, and this also needs to be taken into account, right? When you want to migrate, in our case, is because we don't have the resources. The GPU is not available. You have to migrate to another compute instance, right? So it tells you, okay, I have to migrate. Do you agree? Then you agree. But of course, it can be done automatically, where it migrates automatically without you knowing it. Okay, that will be better. But for Google Colab, you have to ask you. The reason is because it does not migrate the whole thing. It migrates only the notebook. It does not migrate the memory. I mean the folder that we created. But if let's say you can migrate the folder itself, it doesn't have to ask you. Just migrate and then start a new compute instance with the GPU. Okay, that way is the best one. But in our case, he has to ask us first, because otherwise, user will be perplexed by looking at the folder and suddenly the file went missing, right? So it's not ideal case, and Google don't want to confuse the user, so it has to ask you this question. So that's memory migration. Google actually do a partial migration, not complete migration. Okay, and of course, Google already thought very carefully already why they don't want to migrate the whole data or the folder, because your data can be many gigabytes, right? When you start the compute instance, you check at the bottom left, you see it's written 81 gigabyte. You have 81 gigabyte space. Just imagine if you put up the data which is 80 gigabyte, and then when you migrate, you have to migrate this 80 gigabyte from Malaysia to Japan. It takes quite a long time, right? Okay, and it takes a lot of bandwidth. And that's why Google Colab decided not to do that feature. Okay, they just migrate your notebook. It knows that your notebook will not be very big. Okay, your data can be very big. So you have to think about this. When I do the migration, is it worth doing or not? If I were to transfer 80 gigabyte just to do a small thing only, not worth it. You better stay in the same computer to process it, right? Unless this is necessary, where you have no choice, then you have to migrate. Okay? Of course, if let's say it takes a very long time and it costs a lot of money or it costs a lot of time, then you have to change the whole distributed system, so that you don't have to migrate, but you have that resources in place on the site itself. Like for example, in our case here, whenever we create the compute instance, every computer has a GPU. Well, of course, it would be expensive, right? So Google has to invest a lot of GPU for all the machines, and this might not be a viable solution. Okay? Okay, the memory migration protocols, we have store and copy, very simple one. Store and copy means you stop the whole thing and then copy. This is the most simple, but it's very hard to use. It's not saying it's very hard to use. I mean, the experience is not good, because you have to stop the process and then do the migration, start again the process. Just like our Google Colab notebook. You stop the whole thing and then we have to restart the whole thing. Then start a copy. Okay? Another one is concurrent copy. Concurrent copy means this. That means it's going to be automatic. while you are using on this PC, right? And the system find out that you don't have GPU here. For example, in our case, yeah, we use the product, we don't have GPU. Then you have to migrate to another computer, we have GPU. But when you migrate, it doesn't tell you, you migrate automatically. While you're running the program is still running. You migrate into the GPU, and then you use the GPU, and at the same time, you keep on sending the data to complete the migration. Okay? So that is concurrent copy. That means while it is running, you actually do the migration, and this will be seamless. And that is the most the best experience for the user. Because when the migration happens, you do not even know that your process and your data has been migrated to another machine. To you, it's like you're still using the same machine, okay, remote machine. Okay, so that is the hardest to implement, but the most sought after kind of experience for us as a user. Okay, and this concurrent copy actually can be quite costly. Yeah? Because when you transfer, so for example, you're migrating, right? And the data that you transport, okay, sometimes, let's say you get transported, some data here you can change, while the original one not change. Okay? So you have to update it, or you have to update this way. So that is concurrent copy. And it can be very costly because while you are migrating, there are some data that has been changed, you have to go and patch it, okay, to make it consistent for both, right? Another way is to do copy on reference. Copy on reference is slightly different. You migrate, your data might be here, your data might be here, okay? Right? So if let's say your process is already here and you touch some data over here, you have to copy it, right? So you copy when you reference it, okay? You don't copy it when you are not referencing. So most of the data still stay in the original computer, but the data that you touch is going to copy over and then process it on the new PC because your process right now has been migrated to the new. That will be much better. For example, I gave you the example just now. You have 80 gigabyte of data. If you want to migrate the whole thing, it takes time, isn't it? But most of the time when you're running a program, you're touching only a few memory, okay, and not much. Okay, so it will be much more efficient. If you touch that memory, you just copy over one block of memory. If you touch this memory and it's available, you just copy over, right? So by doing that, you're not copying over the whole 80 gigabyte. You're only transporting the data that you touch. So that is copy on reference. It's more efficient. Okay? We will talk about this memory migration more in other chapter. This is just a few examples that I touch. Okay, I'm not sure why this one is here, but that example using CPU only code. Nothing to do with what we're talking about. Maybe it's just to wake you up, eh? Okay, this one we have done this in practical already. With a single CPU, and download the code there, and then this is parallel vector with the GPU. This is chapter 3, so practical 3. Okay, what we have talked about, shared address space, MP, use that. MPI also use that, but MPI also use message passing in order to allow distributed computing. Unlike OMP, you only use on a single system, shared address space. As a mean to actually communicate with one another. Okay, and you can do data parallel computing, and we have touched this a lot of time in our practical. You've got single instruction, multiple data that we process, right? We process the data in parallel. You can run program in parallel, different program in parallel as well. Most of the problems that we are talking about are data parallel. Okay, this is the end of the slide. We move on to the next one. Now the next one is a bit tough for me to explain because I find this slide is very messy and very confusing. I try not to use the slide, but I will come back from time to time to the slide, and I will not go in the order that is given. because it's very hard for me to really explain and make you understand. There are many things to discuss here. Firstly, I'll talk about the synchronization, why we need. Okay. Next, I'll go to a topic called spin lock. Unfortunately, here they use the term not quite right. That term is not quite right. Apology to you all, because this slide actually is quite messy, and another thing is I don't have time to actually amend it, because there are a lot of things to write and create new slides. But I'll explain here. I'm going to talk about why we need synchronization, why is it a problem, and what are we trying to solve. Okay, so the problem is the issue. Okay? And why is it important here? And then the solution. Okay? The solution to overcome this. The solution here, we talk about mutual exclusion. You will see this a lot of time. Mutual exclusion is a solution. And how to implement this. Implementation. And a lot in this slide here is going to talk about it. It starts with mutex, but I'm not going to start with mutex because it's going to be tough for me to make you understand. I'm going to start with spin lock first. Okay, but the slide does not use this name. The slide uses lock. Actually, lock is not a good name to use because the actual name is called spin lock. Lock has another meaning to this. It's related, but there's another meaning. I'll explain to you. So the slide actually write lock. You have to think of it, or maybe you go to the slide and change it. Change it to spin lock because this one is maybe I can go and change because this one is not PDF, right? I can go and change it. But right, we should call it spin lock. Okay, lock is another term related to this, but it has a different meaning. We're going to talk about spin lock first. Then we're going to talk a little bit about maybe binary semaphore. And then I'm going to talk about mutex. Okay, it's something to do with this mutual exclusion. Actually, you can see here, mute, this is mute here, X, this X here. Now, mutual exclusion is a technique. Mutex is an object. Okay, so these two are two different things. This is the technique, this is the object. Okay, these two are quite related. Okay, but there are some differences which is not explained here. Here in this slide, it treats this binary semaphore as mutex. Actually, it's not. These two are two different things. Okay? The slide actually treats them the same. Okay, after that, I'm going to talk about something similar to this called counting semaphore. Not sure whether here I use the term properly or not. Okay, counting semaphore. And counting semaphore has some relation to binary mutex. As a binary semaphore, actually it's the same thing. But that is used for different purposes. Okay? And we're going to talk about it. Okay, problem and issue. I'm going to start with that first. Okay, I'm going to use this slide and then maybe move on to another slide because I'm going to talk about spin lock, right? Okay, synchronization, you have to, why do you need it? You need it because you do parallel processing. Parallel processing means you got multiple process, you got multiple threads, or multiple processor, or multiple core process at the same time, right? If this process don't share data, then no problem. Okay, we don't have problem at all. There's no need for synchronization. But if they share the data, then you have issues. You have to synchronize them. Okay? I'll show you one example, a typical example. What is going to happen? Okay, if let's say we don't synchronize. Okay, two or more execute the instruction simultaneously. This is something that the parallel processing, the meaning of parallel processing is that at least two or more. Each process has its own running state at the same time. They run it. processors have to coordinate the data that they share. Okay? So we have this synchronization issue where the certain part of the code which is critical, okay? You have to protect it. If you don't protect it, you get in trouble. Okay, let's see whether we have an example. Yeah, I'm not going to use this example. Maybe use another example here. Maybe I don't draw here. Let's open up this. So let's say, for example, you have this code here. Let's say array with that, right? You got an array to add, number to add. And you have one sum. Okay? And this one is 2, 3, 4, 5, 6, 7. Okay? Let's say you got one thread, and initially this sum is 0. Okay, thread 1, T0. What it's going to do is it's going to take this 2, sorry, take this 0. And then add 2, and then you will update this. Okay. Right? And let's say T0, T3. That 3 came over. Let's say it comes in this kind of sequence. Right? Because T0 managed to compute and finish this computation and also update it at the same time. Okay? Because we have a read, write, modify. Right? You read the sum, and then you modify it. So it should be read, modify, write. Read, modify, write. Okay? So read, modify, write means you read and then you modify it. In our case, you read 0. You modify it to 2, and then you write it 2. Okay? And T3 came along. T3 means track number 3. You do the task. You take 5, so you take 2 plus 5, 7, and then you update it. Okay? So everything is fine and dandy. So you got 2 plus 5, and you got 7, and this will update to 7. Okay, so no problem up to this part. Okay? But take note that they are sharing the data. So it means, it doesn't mean that when you are parallel computing, you always have this problem. No. It depends on the order of execution, who come first, who come later, or who come at the same time. Now, if they come at the same time, then you're in trouble. If they come at different time, then most probably you don't have problem. But let's say they come at the same time. Let's say T1 and T2 arrive at the same time, and both of them will read this cycle. Okay? At the same time. So in this case, let's say T1 comes along and T2 comes along as well. Both read at the same time. And they get the same data here. Sorry. Same data there. And then T1 is going to add with 3 and T2 is going to add with 4. Okay? So here is going to add with 3, this one is going to add with 4. And you know this one is going to be 10, this one is going to be 11. Right? And let's say T2 right first, then it will be 11 here. And then T1 right later, then it will be 10. But if you look at the whole sequence, let's say you're supposed to do it in sequential, right? The answer should be 2 plus 3 plus 4 plus 5, right? Because T0, T1, T2, T3. Maybe in order, this one is not in order, but the result will be the same, the direction should be the same. But if you execute in order, also it should be the same. So 2 plus 3 will be 5. 5 plus 4, it should be 9. 9 plus 5 will be 14, right? But look at the answer here. 10 is wrong. Even 11 was wrong. Okay, and 10 is wrong. It should be 14 there. So this is one of the problems when you have this kind of parallel computing. Okay? Concurrent execution of program. You get this kind of problem. Okay, how do you overcome it? Okay, this is a problem. We call it race condition. This kind of problem we call race condition. I think I mentioned this many times. Okay, race condition, it means that the thread race with one another, okay, to produce a result, and that result is undeterministic. Undeterministic means every time you write, you have a different result. Alright, for example, I get 10 here, but if let's say T1 write first, then it will write 7 to 10, and then T2 write will be 11. So right now a different result. Okay, it depends on who actually comes first, who comes at the same time, then the problem will happen differently for different scenario. So every time you run a program, the same program, but you get different results always. So this one, it means the result is undeterministic. So race condition will give you undeterministic result. It doesn't say that it's wrong, it's undeterministic. It can be right answer, it can be wrong answer, it can be any answer. Right? Okay, so that is race condition, because everybody is trying to race with one another and they are actually messing up with one another's data. So how do we overcome this? How do we overcome this? Very simple, right? You know, if they come together and execute at the same time, this is the problem. Therefore, to overcome it, you only allow one person or one thread to do at a time. And that is the meaning of mutual exclusion. Okay, mutual exclusion means this. Among the threads, we have mutual understanding. Mutual understanding is we have common understanding. Okay? If I enter, you don't enter. Exclusive. Okay? If I enter, you don't enter. If you enter, I don't enter. Okay, so that's mutual exclusion. Mutual agreement among all the threads. Okay, common understanding among all the threads that we have to mutually exclude one another if one thread already is doing that. So if we allow only one thread to do the job until completion, then we will not have this problem. Because read modify write is actually not a problem. Read modify write is a problem is when they start to compete with one another, racing with one another. Okay, if they can avoid that, then we solve the problem. So the whole story about all this chapter is talking about this only. Okay, and some other part. But the majority of this chapter 4 and chapter 5 is going to talk about this. Okay, the problem is very simple, but the solution you see later on is there are many different ways, and there are a lot of topics to talk about. Okay, we are trying to solve only this problem. Okay, mutual exclusion means mutual understanding among all the threads. When they work together, they have to agree that only one person do the read modify write. You have to wait for the thread to finish the read modify write, then only the other thread can do the same. Okay, so they have to wait for one another, and that's why here we see the synchronization. You have to synchronize, right? Who come first? Who go in first? I mean, who do this first until completion, and then who actually do next. So there is some kind of synchronization that's happening, and that synchronization tools that we use is this, the one that I listed here. Spin lock, binary semaphore, mutex, and then counting semaphore. The counting semaphore is slightly different from the rest. I'll explain a little bit about this. This actually is used for different purposes. The mutual exclusion actually this implementation from here to here. Okay, this one actually is a special case of this binary semaphore, and the usage is slightly different. Okay, let's move on. Now, spin lock. Do I need to use a slide? Let me check. Okay, spin lock is down below. Maybe I can use the picture. Okay, here it's called lock. But what you're trying to say is spin lock, not lock. Lock is a meaning. I'll explain to you. Or maybe I'll explain it now. Now, mutual exclusion. How do we implement this mutual exclusion? We implement it using lock mechanism. Okay? So lock mechanism is a general way to solve this mutual exclusion problem. Okay, so lock is implementing mutual exclusion, is a general name. If you want more detail, what are the different type of locks? The first lock is spin lock. The second type of lock is binary semaphore. The third type of lock is mutex. There are many others, but we'll talk about these three first. Okay, the other one can be later on. I think there will be slide on that. Monitor is one of them, which is used in Java. If you use Java multi-threading, you might have encounter monitor. Okay, so monitor is one type of the lock. So lock is not spin lock. A spin lock is the implementation itself. So when we talk about lock, we're talking about spin lock, binary semaphore, mutex, monitor. Understand? But spin lock is itself a specific implementation of the lock. Okay, so here by right it should be spin lock rather than lock. Now before I go into talking about spin lock, I need to talk about how you do multi-threading or multitasking first. Okay? Because why we come into this parallel computing and concurrent execution and then cause this mutual exclusion problem is because many programs can execute at the same time, right? Okay, so we need to talk about the multitasking first. Now there are two, when we talk about multitasking, I should mention there are two things there. The first one is multiprocessing.
The other one is multitasking. So what's the difference between these two? Multiprocessing means you got multiple processors running the program and sharing the data. And it can cause race condition as well. But they are running on multiple cores. Okay? So your program is running on multiple cores. So this is multiprocessing because there are many processors. Okay? Now how about multitasking? Multitasking has the same concept as multiprocessing, except that you use one processor to run the program. So you don't run in parallel, you run concurrently. What do I mean by that? When I say multi-processing, or multi-core processing, let's say this is the time, right? I got machine 0 or core 0, or I call machine 0, machine 1, machine 2. And this is time. When I execute, all of them execute at the same time. Okay, this is multi-processing. Okay, multi-processing. When I talk about multi-tasking, I'm looking at we talk about one processor first. Of course, you can run multitasking on multiple processors, but let's talk about one processor. I got one processor, but I run the threads. Okay, this is the time, still. But when I run my multitasking, this is going to be my thread 0. I put T0, T1, T2. Because I got one processor, I cannot run all of them at the same time. I have to run them in sequence. So during this period of time, I only run up to this point, from here to here. And then I switch. Okay? And then I use this time to run the code for T1. And then I switch. And then I run using this time. I mean, because I only one processor, right? So during this time, this period of time, I run T0. Then I switch. I run T1. I switch. I run T2. And then I switch again back to T0. I run from here to here. Okay, and I switch again. I run from here to here. I switch again. So basically, I'm switching among this thread and execute a little bit, but I do it very fast. Okay, when I switch in nanosecond, maybe nanosecond or microsecond. And when I execute, also I execute maybe 10 microseconds. But if I do this very, very fast, it looks like all of them running at the same time, right? Okay, this kind of processing we call concurrent processing, concurrency. Okay, this one is called parallel computing. That means we run at the same time. So here, at this time here, I execute on different cores at the same time. Here, no. Here, it gives you the illusion, because it's very fast, it happens very fast, it gives you the illusion that the program is actually running at the same time. Just like, for example, if I open up a browser, open up so many programs and run at the same time, right? You can do this, of course, we know that our processor is multi-core. You can assign different cores, you can do multi-processing. But if let's say I have only one core, we still have the illusion that this program is actually running at the same time, even though there's only one core. Okay? So this one is called concurrency. This one is called parallel computing. Okay? Or parallel execution. This one is concurrent execution. Okay. So how does the one processor do this multitasking? Okay, it has certain properties that needs to be achieved and done in order to allow this concurrency to happen. Okay, so what you do is, whenever you execute this instruction, you save the context of this execution in the memory somewhere. And then when you switch, then you switch the context to T1 and then execute it. What do I mean by that? Let's say maybe talking using this, you don't understand. Let's take a robot. Okay? Let's say a robot, you can buy a robot, let's say in the future we can buy a robot with the AI and everything. And I can buy a module, like some kind of chip where I can put into the robot brain. Okay? So let's say I want to buy only one robot, but I want this robot to do many different things. But the module that they sell to me can only do one task. Either teach the children, you teach your kid to do homework, or the chip can only do cooking, okay? And the other one cleaning, for example. So just imagine that is actually the memory that remember all these tasks or all these track context. So as you install into the robot, then it knows, okay, right now I know how to cook, but I do not know how to do anything else, only cooking. When you remove it and you put in another one, that one is to teach your children maybe, okay? Maybe do their homework or whatever. And another one, when you install, it knows how to clean the house, but it doesn't know how to cook, doesn't know how to teach your children. So you just imagine that the processor is doing that very, very fast to all this on the same PC, because one processor only, right? So you install it and it knows how to execute this. And then you remove it, save it somewhere, and then take another one, another of this module, put it into the processor, and then you understand how to execute it. So you do this very, very quickly, okay? But what I'm trying to say here is the context. The context that I was talking about there, where it remembers when or how or where actually it has already run, or the data that is already computed is saved inside somewhere. Okay? So that is, we call it context, okay? Or track context. The context is just like a memory. It remembers where it was before, so that it can continue to execute at a particular time. But when you switch, then you cannot remember anything like this. And when you install the T1 context, then it knows about the T1 context. It doesn't know the rest. Okay, and then you switch. Okay, so that is track context. Right. Now I'm ready to talk about speed lock. Okay, after talking about this, now we talk about speed lock. Okay, suppose you don't have multiprocessing. We talk about multi-threading first. Of course, we'll apply to multiprocessing, but let's talk about multi-threading first. I want to implement mutual exclusion. Okay? And mutual exclusion, you know that only one process or one thread can enter, do the read, modify write. While that thread is doing that, the rest cannot. Okay? So somehow you need to lock, isn't it? You have to lock, isn't it? So one thread enter, you lock. Just like locking the door, and then do the process. When it's done, unlock the door, then the next thread will come, will lock the door, and then do the job. And then when you come up, you unlock the door. Okay, so you have only one key, and once the person has the key, you lock, nobody else can enter. Just imagine that. Right? Okay, so what's the problem here? The problem is you have to wait for that lock. Right? So you have T1, T0, T1, T2. Everybody is waiting for that key. So what does it do? You have to check. Is the key available or not? And you have to check constantly. Okay, I check now, don't have. I check again, don't have. I check again, don't have. Okay, until you have it, then you grab the key and then you unlock it, enter, do the job, exit, and then pass back, give back the key. Right? Now the process of checking, just to get that key, you have to write a code something like this. Wow. Check the key. Right? If the key is, I have to put a note there. I mean no key. Okay, the return no key. If no key, you wait. If there's a key, then only pass on, and then you get past this line, and then you execute the code, and then return the key. Is it correct? So this while here, it's actually the code is just spinning here. That's why it's called spin lock. Okay, the while loop because the code keep on checking, right? Okay, so that's the reading of the meaning of the spin lock. Spin lock actually comes from here. Keep on checking, right? Okay, let's have a look at multi-threading. Now, who actually do this switching here? Or who decides switching? Who actually do switching is the processor. The processor do the switching. But who decides the switching? The person who decides the switching is your operating system. In our case, in Windows, or in Linux, the Linux operating system. You will decide when to switch it. And of course, you have to choose certain period of time, not too long, not too short. If you switch too many times, you waste time switching rather than doing useful job, right? If you make it too long, then for the user will find out it's a bit like not concurrent, right? Because maybe you spend 1 second here, another 1 second here, another 1 second here. So you feel like the program doesn't run very smoothly. The video is not smooth, for example, right? So what you prefer is very short time, maybe in millisecond or maybe in microsecond. Okay, maybe we choose, let's say, 10 microsecond here, 10 microsecond here, 10 microsecond here. So every 10 microsecond, the operating system will decide to switch to another track and execute it and do it very fast. So by doing that, then you have finer granularity, and you have a better experience because everything looks smooth. Is it correct? Right? And that time we have a name for it. It's not inside the slide. It's called time quanta or time quantum. Okay, the operating system will decide. Most probably in maybe 100 microseconds. So 100 microseconds, 100 microseconds, 100 microseconds. Now the operating system can decide. This one 100 microseconds, this one 50 microseconds, this one 10 microseconds. Can decide. Depends on the priority. The higher priority may be larger, small priority is smaller. But that one is depending on the scheme, the multitasking scheme used by the operating system. But most of the time, it will be the same. Okay? Now let's choose one time quanta. Let's say 10 microseconds. Okay? 10 microseconds. Now, suppose T0 counts, we execute right now because you got one processor, you're doing concurrent execution. T0 was given 10 microseconds, and then you speed. Okay? You know that why do we need a speed? Because you need to find out whether the key is there. But let's say the key is there, then you can immediately get the key and do the job, no problem. Right? That means you're lucky. But what happens if the key is not there? What happens if the key is not there? Then the guy have to spin, right? You have to spin for how long? Don't say that. I already mentioned to you, 10 microseconds is the time quanta. You have to spin for 10 microseconds at most. Because it cannot get the key, right? Right. Why you have to wait for 10 microseconds? Suppose T1 is the one that holding the key, right? He is the one holding the key. But the processor cannot execute it. That means it cannot return the key. That means this T0 have to spin for as long as the time quanta is given to it. If let's say it cannot find the key is not there. Alright. Because let's say T0 hold the key. And it cannot do anything because it's not running. It cannot return the key. Right? So this T0 have to spin for no purpose. You have to spin and waste that time quanta. Okay? And then T1, when you switch to T1, and T1 also look for the key, and he has to waste that 10 microseconds again. Okay? Now, when you switch to T2, now T2, because he has the key, let's say for example, now he can start to execute it and return the key. Let's say he managed to do all the job. Yeah, mutual exclusion, can do all the job, and return the key in 10 microseconds. So right now, when you switch back to T0, now T0 can get the key already. You understand? Okay, what do we see the problem here? Spin lock actually solved the mutual exclusion because with the key, only one person can enter and do the job. Okay, so it solved this problem earlier on, what I mentioned to you, right? You will not have race condition because lock will implement mutual exclusion. But what is the problem with the spin lock here? Spin lock here is you have to waste your time. Okay? Now, how do you overcome this? How do you not waste this time? Can you have a way where if you find there's no key, you don't have to waste your time quanta. Okay? You ask the operating system to switch immediately. Okay? So instead of wasting spinning there, you have the key, and you tell the operating system, I have nowhere to go. I don't want to spin. I don't want to go. So the operating system, okay, you go to sleep. Okay, and I switch to T1. And T1 try to access the key, and it cannot find the key. It does not spin also. You just say, tell operating system, okay, I'm not going to spin. I cannot find the key. Okay, and then the operating system will switch again to T2. Right now, you can escape. So right now, you don't waste time, right? Fair enough? Okay? So how do you do that? You have to use another kind of lock. And that lock is this lock here. Binary semaphore and index. These two can do that. Okay? So spin lock actually is not good because you have to spend the time spinning, waiting for it, and you cannot get the key anyhow because T2 cannot execute. Okay, if let's say T2 was holding it, you cannot execute. If let's say nobody holds it, then you're lucky, no problem. But you're unlucky, somebody holds it. You have to wait until the task switching happens, okay, until the processor executes the thread that is holding the key. Until it returns, then only you can receive it. Otherwise, everybody has to spin for no reason, wasting the time. You understand? Okay? Now, in order to overcome that, you need a mechanism, another kind of lock where when you cannot get the key, the operating system will know that, and then you put it to sleep. Okay, put it to sleep, and then switch it to another thread to execute. So by doing that, you are not wasting time. Okay? Now, if you're wondering why do you create spin lock if let's say it's not so good? Okay, spin lock is good actually, but good for another purpose. These two, it can solve for single processor very efficiently, right? But it cannot solve this problem. Okay, this also will have race condition, just that a different way of race condition. This race condition is using one processor, you have race condition, but this is multiprocessor can have race condition as well, and these two cannot solve it. You have to use spin lock. Okay, why? Okay, let's say for example, let's say M2 is holding the lock. Okay? And what you do is you spin here. Okay? Spin until this M2 releases it, but M2 can release it while it is spinning. It is actually not wasting time there. Why? Because these processors are running at the same time. You see that? So anytime it can release it. Okay? So when it releases it, then M0 can receive the key immediately. So it is very useful for multiprocessing, but not so useful for multitasking. Okay, for multitasking, we prefer to have binary semaphore or mutex because it's more efficient. But when we are talking about multiprocessing, actually these two will not be able to solve it. I'm not going to go into it, why, because it cannot solve. But you have to trust me, it cannot solve the problem. So we have to use spin lock. Whenever we have multiprocessing, don't think about binary semaphore, it cannot solve. You have to use spin lock always. Okay? But spin lock solves this efficiently, but not this. Okay? And spin lock normally is used for very short wait. You don't want to wait for too long. For example, you spin, and those who have the key do the job must be very quick. Okay, very little job to do. Okay, lock quickly, you return back the key. So by doing that, then this all the processors that is waiting is going to spin for a very short period of time. Okay, so if let's say you know that the task is going to be very lengthy, then you have to reorganize your code so that you can break it down into multiple steps. And you spin a little bit, and then you release, and then you try to acquire the lock again, and then spin again. Okay, if let's say you fail to receive the lock. Okay, so spin lock is good for multiprocessing, but not good for multi-threading. But the purpose is the same. Okay, so let's look at this two. I'm going to talk about maybe just the feature, because this two is the same when it comes to telling the operating system that it cannot find the key, that means the key is not available. Okay, and the operating system, what it does is, it will block this track, okay, waiting on the binary semaphore or the mutex. So there's a queue. Let's say this is a binary semaphore. I went on ES, binary semaphore. There's a queue. So let's say T1 try to acquire the lock, but it doesn't have. The lock is occupied and is used. The operating system is going to block this track so that it cannot run. But when it blocks, it will put it into the queue. Why does it need to put it into the queue? It's because when the key is returned, then the operating system will remember who to actually wake up or who to actually let it run. Right. And also, the queue actually in sequence, meaning that if T1 comes first, then he will be served first. If T2 comes, you go at the back at the queue. So the operating system can also synchronize, not only know who actually to let it execute, but in which order. Because who comes first come first served, right? So if you put in the queue like this, then all the tracks that's waiting before, okay, it will be blocked under this binary semaphore on mutex. Mutex also has the same thing. Okay? So they'll be waiting there, and then they'll pass switch to the next track without the track to spin. There's no spinning here. Okay? Whenever there's no key, you will go into the queue straight away, and then get locked. Okay? And the operating system knows that you cannot run anymore. You touch switch to the next track. So the processing time is not wasted. Is that clear? Okay, so there's the difference between spin lock and binary. But then it performs the same task. It performs the mutual exclusion. Remember, if there's no key, you have to wait, right? One is to spin, the other one is to block. Okay? And because only one person can get the key, and when can that happen? Let's say T2 is the one that holds the key. When it return that key, the operating system will look at the queue. Okay, the queue related to that binary semaphore on the index. So you look at the front, the queue is T0. So you release this T0, let it run, and give it the key. Right? So when you get the key, you can actually go open the door and do the job, and then once it's finished, you return. And then the operating system will pass to T1. So eventually, everybody has a chance to execute, but all of them will execute in synchronization, one by one after another. And they'll do read, modify, write to completion before it actually pass the key to the rest. Okay? So all of them actually solve mutual exclusion, but the way they handle things is different. Okay. Next, I want to talk about the difference between these two. They look alike, but they are quite different. They're different in the sense that mutex has what is known as ownership. Okay, ownership means if track 0 acquire it, that means able to lock it, then this mutex temporarily belong to T2. Let's say T2 managed to lock it, then T2 will own it. Okay? So this ownership actually has make these two different. Because binary semaphore, there's no ownership. You cannot own anything. Okay? So mutex you can own. So the operating system can check who actually owns this mutex, who actually hold the key. Okay? For binary semaphore, the operating system cannot find out this. You cannot find out this information. Right? Now, why do you need this ownership? Because the because of programmer. As a programmer, we all make mistakes, right? Okay, and the operating system designer, when they create all this feature, mutex and all that, they let the developer use it, and they find out that the developer they are not disciplined, always program in a way very funny, and then get themselves into trouble. Okay. One of the problems is if you don't do it properly, you get into a situation called deadlock. I'm going to talk about it later. Deadlock. If you don't use it properly, why is it deadlock? I'll explain later. if you don't use it properly, you get into this kind of situation. Deadlock means I lock and the other person lock. Okay? And right now, nobody can progress. Because I lock you, you lock me. And I cannot progress, you also cannot progress. That means I cannot release, you also cannot release. Right? So deadlock means both of us get locked and we cannot get out. Meaning that right now, we cannot progress at all. And this is a serious issue. When you come into deadlock, you cannot progress, that means the program cannot run at all. Okay? So, but then Mutex has ownership. So ownership means this: if I lock, then the operating system knows that you lock this Mutex, right? Then who is able to unlock it? Is the owner of this Mutex that can unlock. Okay? Now the problem with deadlock is this: because there's no ownership, anybody can lock it. So they lock one another. Okay? With ownership, then the operating system will only allow the owner to unlock. If you lock it, you can unlock it. But if you don't own it, you cannot unlock. If you unlock, then you get into this kind of situation. Okay? So that is the difference between binary semaphore and Mutex. Now, why do you have a binary semaphore if, let's say, Mutex do all the job? Okay? The problem is, with Mutex, you cannot do signaling. Okay? There's another problem that we are going to talk about. First problem is this problem, and the solution is mutual exclusion. Right? Another problem that we want to talk about is synchronization using signaling. Okay? This one I'm going to talk about it later. So binary semaphore can do signaling, but Mutex cannot. The reason why it cannot is because he has ownership. Okay? Once he has ownership, he cannot do signaling. So in that case, we need both. We need binary semaphore, we also need Mutex. Right? So binary semaphore and Mutex actually is quite similar, except that these are the difference. Binary semaphore not only can do mutual exclusion, it can also do signaling. Mutex, it can do only mutual exclusion, but it cannot do signaling. Okay? Okay, so that is the trick. Now the final one is a bit harder for me to explain. I'll explain later. Okay, let's get back to this slide. Let's see whether I can use this slide. Okay, let's move on to producer consumers. Okay, I don't want to go into producer consumer straight away because if I go into that, I have to talk about counting semaphore and also talk about Mutex at the same time. So I try to delay that for a while. Okay, I think I go into this counting semaphore first before I go into other solution. Okay, I'm not going to talk about that Peterson algorithm first. I'm going to talk about counting semaphore. Okay, why do we need counting semaphore? Counting actually, okay, before I go into counting semaphore, let's look at the binary semaphore first. Because binary semaphore is actually a counting semaphore with the number of 1. Okay, how do we implement binary semaphore? We implement it using a counter. Okay, there's a counter, and it has the ability to get blocked, right? So For a binary semaphore, let's call it a binary semaphore. The counter, when we start with a value of 1. We start with value of 1. Okay? And how does it solve this mutual exclusion? Okay, first thing is the step. The step is like this. Okay, here you use the term. Okay, binary semaphore. Let's say I create a semaphore. I call it semaphore. In code, I write like this. Semaphore. And then I set it to 1. Or maybe in object orientation, this is an object, and we pass the initial value inside that. Okay, let's talk about C++. Okay, C++ we can do like this. So our initial value is 1. The counter is 1. Right? Now, how does the semaphore work? Before we access into the door, into the room through the lock, we have to perform a down. Okay, so we do this down. Okay, down means you reduce this from 1 to 0. Now, if it is 0, that means there's no key. If it is 1, there is 1 key. Okay? So you just imagine the number here, counter, is to tell you whether you have the key or you don't have the key. Okay? So if it is 1, when you perform a down, you see a 1, that means you can pass. Okay? Because right now it becomes 0 already because you take the key, right? So it becomes 0. So the next pass that's coming, or the next track that's coming, when you perform a down, you see a 0, so you get blocked. Okay? Right? So our code will be something like this. Whoever going to do the read modify write, okay, it will have to do a down first. Okay? If the counter was on 1, then it becomes 0 and it get passed. That means the guy has a key and he can execute immediately the read modify write. Okay? So here the code here that it does the read modify write, we call it the critical region or critical section. Why is it called this way? Because this is the critical one. These are the ones that you need to synchronize. If you don't synchronize, you get into race condition. You need to have mutual exclusion. Mutual exclusion is provided by binary semaphore by doing a down first. Okay, if you have a key, which is 1, then you get passed and you enter into a critical section to do your read modify run. Okay? Now, when you're done, then you do semaphore up. That means from 0, get back to 1. Because you release the key. Yeah? You release the key, then you do an up. So now when it does the up, now the counter get to 1, right? Whoever that get blocked here, the operating system will go to the queue and then release it. Now, if thread 0 was there, then it get released, you will enter into the critical section right now. Okay? And of course, when it get into the critical section, the operating system will give it the key. So it has the key right now. You can enter into the critical section. But T1, who was also get blocked, will still remain in this queue. It will not execute. It will get blocked still. Okay, you cannot enter the critical section. Only T0 can enter. Now, when T0 finishes, right? You perform an up. Now the counter from 0 will become 1. Okay, the operating system sees there's a key. You will unblock this T1, and then let the T1 to enter. So right now, you can see the operating system is synchronizing all the threads. Although they come at the same time, but they will all end up in the queue except one. Okay, except one that will execute the critical section. And when it is done, it will do an up, and that up will cause one of them to be unblocked. And then the operating system will allow them to enter, while the rest has to wait. And then when it finishes, you do an up, and then you return the key, the operating system will choose the next to unblock. Do you see the process? Okay? So this is how binary semaphore is used by the operating system to synchronize multi-threads that's coming in at the same time, and then it tries to synchronize them, allowing only one mutual exclusion, only want to enter at one time, and disallow the rest waiting in the queue until it is time for it to execute. So the operating system will watch the key, the semaphore key, which is whether it is a 1 or 0. If it is a 1, that means there's a key. If it is a 0, then it has to wait. Okay? Is that clear? Now, the mutex is also the same key. Actually has a counter inside there as well. It performs exactly the same like binary semaphore, except that it has the ownership. Maybe you don't understand the ownership, I'll explain to you later. Okay? When I have more time to explain and more free time to discuss about it. So, binary semaphore and mutex, more or less the same. It will be something like this. Okay? So the mutex, the way we write it, we got mutex. I'm going to write it here. How do we write it? We got mutex. And let's call it mute. Okay, here we don't have any 1 or 0 because mutex is always only 1. The counter is always only 1. Okay? For semaphore, normally we talk about counting semaphore, and this is a special type of counting semaphore. We can set the value. It can be any number. If any number bigger than 1, okay, any number bigger than 1, then it becomes counting semaphore. If it is a 1, it becomes binary semaphore automatically. Okay? So we can choose between these two. For mutex, the counter is always 1, so we cannot adjust it. Okay? So mutex is like that, and then when we do mutex, normally we do it. Mutex acquire. Acquire means you try to acquire the key or acquire the block. And then you do the critical section here. Okay, critical section or your critical region. Critical, why is it called critical? Because this is the code that requires mutual exclusion. And then you do mutex, release. Okay, the name is different, acquire, release. Here we call down or up. Okay, just the terminology that is different. Okay, although they look alike, but they are two different entities. Okay, now there's another. If you look at this slide, they don't use this name. Okay, in this slide, I think they use here they use weight. Also the same. Some implementation we call it weight. The original one they call down and up. Okay. This one is by the inventor. The inventor who decided to use down and up. But after time progressed, people find out down and up doesn't make sense. So they use this term for down. They call it wait. Make more sense, right? Because if you cannot get the key, you have to wait. That's why it's called wait. And then here is signal. Okay, when you do up, you signal the rest to wake up. Okay. That means you signal to not the rest, the front of the cube to wake up, or the front of the cube to unblock. So you wait or you signal. Okay? So this is a term that is used, but the meaning is the same. Okay, if you see this is the old terminology. If you see this is a modern one. And they might use a different name. Some might use similar name like this. For example, semaphore, they call it acquire, they also call it release. It can be something like this, because they look alike, right? But these are the terminology that they use. But the meaning is the same for all. Okay? So that is how the binary semaphore and mutex works. Okay. Now let's talk about counting semaphore. Okay, in counting semaphore, the number here or the counter can be any value when you start. It can be any value. It can be 10, it can be 20, or it can be 100, or it can be 1. Or it can be 0 even, but it cannot be a negative number. It's always positive number or 0. And it can be 0. Okay, there's one thing that I forgot to tell you, but I think I'll leave it to later to explain. You can start with 0. Why you can start with 0? There's some usage for that. Okay, the counting semaphore, you can start with any number. Okay? So what is the purpose of that? The purpose of it is not mutual exclusion, no. The purpose is to control how many threads can enter. Okay? But of course, it cannot solve mutual race condition.
the purpose is not to solve risk condition when you are using counting semaphore. Is to count how many is able to enter into this section of the code here. Okay? Now if I put 3, that means 3 can enter at the same time. Okay? So if the fourth one comes, you have to wait. You wait in a queue. Until one person left and release it, you signal or you perform an up, then only you will be unblocked and then you enter. So only 3 at a time, if the counter is 3, only 3 at a time can be inside this section. Okay? But then it doesn't solve the mutual exclusion. Okay? Now, what happens if, let's say, the person is, the thread is not able to enter? Okay, let's say it's 3 and 3 is already in, the fourth one comes in, you will be blocked. Okay, you will be blocked until somebody release, and then you will be unblocked, and then you enter. So when you enter, you will be 3 back inside there, right? So 3 at a time. Now let's see why we need this kind of feature. We need that feature is because we want to solve this producer-consumer problem. This one. Okay? Producer-consumer problem. It's a classical synchronization problem. All right? Okay, the idea is this. If, let's say, for example, I have a message to send. Okay? I have a message to send, let's say a pipe or something like that. If the sender, or the producer, we call it, producer in this case, or the sender, is very, very fast. Okay? Faster than the receiver. What we want is to have a buffer in between. If, let's say, for example, the receiver is as fast as the producer, do you think that we need a buffer? Okay, let's say, for example, I can produce information 100 information per second. This guy also can process and receive 100 messages per second. Do you think you need a buffer here? No, you don't need it, right? Because they are at the same speed, right? Whatever you produce, I can receive it. But what happens if, let's say, for example, this is sometimes slower, sometimes fast. It's also the same thing, sometimes slow, sometimes fast. Let's say, for example, when it is fast, it's sending at full speed, but this guy is slow. What happened to the messages? Some messages get through, he is processing, but because it's faster, the next one that comes will disappear. Because I sent to you, you're not ready to receive, right? So where does it go? Get thrown away. And get thrown away is not a good thing. Because when you get thrown away, the data is lost. Alright. So how do you overcome this? You put a buffer in between. Okay, the name buffer means you try to be a little bit, like a sponge, right? You can receive the water to retain it, right? So the same thing here. When you're buffering the message. So if, let's say, the receiver is a bit slow at some particular time, and the producer is faster, then you fill up this buffer, right? And why you fill it up? Because you don't want the data to be lost. If there's not, the receiver has no time to process it, you get buffer here. It's not lost. When it is ready, then you take the data out. So that is the use of this buffer. So that we can retain the data, we do not, the data does not go missing if the receiver is slower. Okay? So it can be something like this. I'm a bit slower, then you get filled up. But when I gain my speed, I'll start to retrieve the data. So it will clear up the buffer. So you can see the buffer go up and down, up and down. Because the producer sometimes fast, sometimes slow. The receiver sometimes fast, sometimes slow. And how much the size that you determine for the buffer
is the rate difference, the maximum rate difference, right? Because eventually, if let's say the producer is in a burst, it produces very fast in a burst, it can overflow, isn't it? Is that true? Because this buffer is finite. The one overflow is going to be loss. So you have to choose this buffer size very nicely. You understand? Okay. Now, how to choose this buffer? We are not interested in this topic. So this one is another topic. If let's say you want to implement buffer, you have to choose depending on what is the fastest burst of this producer, and what is the fastest burst to receive it. Then you calculate the difference. Then you determine the buffer size. But that is not the topic of today. We are not going to talk about that. We are going to talk about how the producer and the receiver synchronize. Because if you don't synchronize, you have race condition problem as well. Okay? For example, when I touch the data, I'm going to override it, but the producer is also modifying and update it. Okay? Modify and write. And then when both try to write at the same time without mutual exclusion, you find out that there is race condition and they override one another and the data become inconsistent. Okay? So that is a topic of what we are going to talk about. But the buffer thing, I talk about buffer is just to explain to you what is the producer, consumer in this case, what do we need and why do we have a buffer. Okay, so right now we want to talk about, we have this, but how do we overcome the problem that I mentioned to you? We have producer and consumer. Both of them are trying to write into this. Somehow, you face race condition. Okay? Okay, there are two things that you can face. One is race condition. The other one is the overflowing problem. Remember I told you that the producer, you can produce faster, isn't it? Okay? Then you overflow, but if you don't stop it, the data will go missing. Okay? So how do you stop this producer when the buffer is full? Counting semaphore. Okay? So the counting semaphore is not solving mutual exclusion, although there's a mutual exclusion problem here, but the counting semaphore is to solve this other problem. This buffer here can be filled up, but somehow it will get full. Right? And you don't want it to after it's full, you don't want the producer to keep on putting in the data because the data or the message that comes in after it's full is going to go missing. You want to stop this producer, block this producer from producing further. Wait until the receiver retrieve one. When you retrieve one, you got one slot empty, right? Now the producer can put in another one. Okay, but one is filled up, you will get blocked again. Okay? So you can see the blocking just now. The blocking is something similar like the mutual exclusion problem just now that I was talking about. Okay? You get blocked if there's no key. In here, you get blocked if there's no slot. Okay? And why it is counting semaphore? The number is bigger than 1. And actually the number depends on how many slots that you have here. Okay? So if let's say 1, 2, 3, 4, 5, 6, 7, 8. If I have 8 slots, my counting semaphore, let's call it CS, it will start with 8. Okay? You start with 8. Now, if the producer produce 1 and use up 1, you will perform a down from 8 to 7. Now you have 7. Right? Then eventually when you fill up, it will be 0, isn't it? Is that true? It will be 0. But if I perform a down first, before I'm able to put a new one, right? I have to perform a down. So when it's 0, I perform a down, then I get blocked. Because there's no more slot. So the counting semaphore is not used for mutual exclusion, it's used for this kind of problem. So if I get from 8 down to 0, I'm able to put in nicely. But from 0, I try to perform a down, the producer perform a down, we go to the blocking state. Now the operating system will queue it up in this semaphore, okay, and waiting for the receiver to release it. Okay? So how does the receiver release? First, it will use up this message first. When you use up the message, what will happen? You will have one empty slot, right? Okay? Then the receiver will help the producer. You tell the producer, you perform an up one time. So when you perform an up, it from 0 to become 1. Now it sees that there's one slot, then you try to produce it and fill it in. Okay? So that's how the counting semaphore is used by the producers. Okay? To count how many slots that is empty, so that you can fill in. But once this empty slot is finished, no more, it's full already, then it has to be blocked. And the only way for it to be unblocked is by the receiver. The receiver will help the producer to unblock. Okay? Now, there's another problem also on the receiver side, similar problem on the receiver side. Just now I talked about producer, right? The receiver also has a problem. What if the buffer is, okay, let's say the buffer is full. If the buffer is full, if the receiver retrieves the data, should you block the receiver? No, right? Because you've got data inside there to retrieve, so you shouldn't block it. But what happens if, let's say, the buffer is empty? No more data inside there. And the receiver tries to receive the data in the process. You cannot let the process to proceed to process that data because there's no data. You have to block the receiver, isn't it? Okay? So you need another counting semaphore. So you need two counting semaphore. One is on the producer. Okay, you start with 8. Let's say you've got 8 slots. Initially it's empty, that's why you start with 8. 8 here means there are 8 empty slots. Okay? On the receiver side, you also have to have a counting semaphore. Okay? The maximum is also 8, but the starting value is 0. Okay, so this is how we write the counting semaphore. Okay, we call it, okay, let's call it semaphore rather than counting semaphore because both of them are the same. Semaphore. Okay, so we start with this semaphore and we put a number 8, 0. Maybe let's call it, let's say, let's call this full. Okay? Full 8, 8. The maximum value is 8, and my initial value is 8. That is used by the producer. The producer is going to use this semaphore. Okay, it's a counting semaphore because it's 8, and the initial value is 8. Okay, and the receiver is going to have another one, its own one. Because we also have to control the receiver as well. We cannot let it retrieve the data if the data is not inside this buffer. Okay, it's empty, let's say. Let's call this empty. And we start with 8. The maximum value is 8, that means we got 8 here. But the value that we start is 0. Why do we start with 0? Because when we start, the buffer is empty, isn't it? Yeah, the buffer is empty, so it should start with 0. How about the producer? When you start it, the buffer is empty. Right. But then because it's empty, it has 8 slots to fill in. That's why it starts with 8. You cannot block it, because 0, you are blocking it. With 8, you have 8 down before you get blocked. You start with 0, you perform down, you get blocked straight away. And you want it for the receiver because there's empty. When you perform a down, it should be blocked. You want that, right? But for the receiver, you have to start with 8 because you got 8 empty slots. If you perform a down, it will be 7 because you use up 1, right? So you fill up 1, 7 left. And you still can fill in because you got 7 left. Until it comes 0, then it's full. Okay, so full here is used by the producer to do that kind of synchronization. Okay, so we start with that. Now let's see how we write the program. Okay, we're going to have the buffer, and let's assume that this is the object in C++, and we have the slot. Okay, Okay, we have a slot here. And we put that index number here to indicate which slot that we want to put in. Is that right? Okay, let's say this is slot 0. Maybe here, start here, slot 0, 1, 2, 3, 4, 5, 6, 7. Right? And this number here corresponds to the index number here, which slot that you're supposed to put in. Okay, and the buffer also will have a counter. Now this counter is different from this counter. This is a counter in the semaphore. This counter also is a counter there also in the semaphore. But this counter is the buffer itself. And I'll explain why we put it in, is so that it simplifies our programming. Okay? So this counter, we're going to start with 7. Start with 8. Okay, so the buffer is an object. Okay, it keeps track of how many inside. Okay? Maybe I should call it, give a different name rather than counter. Let's call it empty slot. Okay, empty slot is 8, that means I got 8 empty slots. Okay, so it's a counter keeping track of how many there. So the process is this. If I'm a producer, okay, I will look at the empty slot, right? And if there's if it is not 0, that means I can add the value inside there. Okay, I can add a message inside there. And then I reduce this empty slot by 1. Then it becomes 7. Okay, so it's actually also counting. It's also counting. So this is counting used by the operating system. This one is used by our own self, our own program. Okay? Alright. Okay, and we also need something else. We need this in and out. Let's call it integer. In and out. Index in, index out. And this in, we start with a 0. And this in variable is used by the producer. So this in here is the index number that we're going to use. If we start from 0, that means we're starting from there. Right? So if I have a message, you go to index number 0 because in indicator is 0. So you go to this slot. So once I get into this slot, I have to increment it to 1. So that right now, I'm pointing at this next available slot. Okay? Give you 1. Okay, let's say for example, initially it was 0. After I add in, it will become 1. If I add in more, then you will move it to 2. But of course, somehow, it will become 8, right? It become 8. Then you have to wrap around. You cannot proceed because there's no more buffer there. You have to wrap around to become 0. So 8 becomes 0, 9 becomes 1. Okay, why do we need to do that? Okay, let's see this. Why do we need to wrap around? If let's say, for example, I put in, because this is finite, right? I put in the data, put, fill in, finish. Okay, so this is the producer, and here is the consumer. For the consumer, when I receive the data, do I receive from the 7 or I receive from the 0 first? I receive from the 0 first, right? Because this is first come, first serve, right? If the message comes in, it goes to the 0 first, right? And then proceed on to the next slot. The consumer, when I consume it, I cannot start from 7, I have to start from 0 also, right? So I will have, my consumer also will have a variable called out. And it starts from 0 as well. Okay? Now let's see. Suppose the producer is fast. It starts from 0, pointing here. You put the data, right? And then it moved, the in will move to the next one. And if I have data, I put it in, and the in will move to 2, put it in. Eventually, in will be 7. And I use up the last one, and in will be 8, finally. Yeah? That means it's full right now. Okay? In will be 8 at that time. How about out? Out will be still 0 because the receiver hasn't had the chance to receive it. You have time? About 8 minutes. Okay, but right now, the consumer is ready to receive. Okay? So when I receive, I'll receive the first one. So that's why it's 0. So you get it from here. So when you get it from here, this one will be 1. Is it? So out actually, so in should be 8 right now. Out should be 1. It should be here. That means here is empty, isn't it? Is it empty? So here 8 actually should wrap around here because it should put it down here. So that's why this 8 should be go back to 0. So you have to, after it goes to 7, you have to get back to it. So that when I receive it, I receive the data, my out is going to be 1, okay? And now the in is going to be 0, and I can put it, because I got one empty slot there. You understand? Now to implement this wraparound is very simple. What you need to do is this. I showed to you how it is implemented first, and then later on you get a better picture. So I'm going to perform this first. I'm going to buffer. Let's say I put the value right. I'm going to put buffer. Yes. I'm going to have buffer. Yeah, this one's good. Buffer slot. And in, I put the data inside. Okay? Put the data in this slot. Let's say it's 0. Okay? And what next I need to do is I do this in equals to in plus 1, right? So they increment by 1. But we have to take care also that it's going to wrap around to here. If you go past 7. Okay? Now in order to wrap around, you do like this. Percentage, that means you are doing, what do you call this? The percentage? Huh?
Modulus.
Yeah, modulus. What modulus number should you put here? 8, isn't it?
Yes.
Is it 8?
Yes.
Because 7 modulus with 8 is 7. 8 modulus with 8 is 0. Then right now it wrap around to 0. Okay? So when I do this slot, I should be doing this. Okay? I should do the in and then I wrap around. Okay. But before I'm able to put the data in, I have to do the down first. What I do? Full down. Is that logical? Remember, this semaphore is going to keep track also with this count, this number of slots. Initially, it starts with 8. Right? If you perform down, you use up the slot, you increment the index number, and you come in again, you perform a down, eventually you fill up, right? Right? Now, if you perform some more, if the receiver is not receiving it and is already full, you'll be blocked. You will be prevented from adding a new one. Is that true? Right? Let's say you reach 7 already at the moment. You reach 7. You put the data in already. The next time when you come in, because it's full, when you perform a down, the counter is 0 already because it's full, right? So here is going to be, the counter is going to be 0. If you perform a down, you're going to be blocked. Understand? If it is not blocked, you get past, that means you got still empty slot and you can add in still. Okay? Now, when it reaches this 7, let's say 7, right now 7, put the data, 7, and then when you increment to 8, right, it will be models with 8, and right now it becomes 0. So, in will be ready to put it to 0. But then, if you perform a down, you'll be blocked. It's waiting here, but the next producer producing of this data is going to block because the receiver hasn't received it yet. Is that clear? So up to this point, you get it? Okay? So you perform a down, and then you put the data in, then you update the in. And you also have to adjust it so that you wrap around. Okay. How about the receiver? Let's look at the receiver. Or the consumer. So this is the producer. And this is the consumer. The consumer also the same thing. But instead of doing a full down, I do an empty down. I perform an empty down. But what happens if I perform an empty down when I start with a 0? If I start with a 0 and I do a down, will I get blocked? I will get blocked, isn't it? But then if you look at the producer never do anything. So you get blocked because you start from 0. So what you have to do here, which is missing right now, you can see already, when you perform full down, is to actually find out whether is it full or not. If it is full, you get blocked. If it is not full, you get passed and then you fail it. But at the same time, you also have to tell the consumer, right now you got one, at least one slot that is not empty. So you have to do something this empty. Is that clear? Is that clear? So here you do a down because you want to find out whether you're full or not. But when you do it up here, you're actually telling the producer you got one slot. I already put in here the data. So I perform an up. Right? So let's see here. Suppose the consumer does not receive anything. Only the producer is fast. So it's going to perform a down. Down is 8, down to 7. You put in the data into slot 0, and in will increment to 1. Okay? And then you perform an up on this empty. So from 0 it becomes 1. Right? So that when the consumer tries to receive it, it can actually progress. It will not get blocked. Because you got at least one slot that is full. Okay? And then when the producer produces some more, another down, and then you keep on moving until you fill up. So by the time you fill up, this full is going to be, the counter is going to be 0. Right? How about the empty? The counter is going to be the maximum, which is 8. Right? So if the producer is faster and you fill up all this, the full is going to be 0, the empty is going to be 8, because you keep on adding it. Okay? So adding it 8 times and you get 8. So this consumer here can call this function 8 times at least before it gets blocked. Is that true? Okay, so how does it do inside here? When you receive like this. This is my data that I want to receive. Buffer, slot, out. This time is out. And I also update my out using this +1 and percentage. Okay, the reason why I need to do modulus as well, because my out is also moving, and eventually when it hit 8, it has to wrap around as well. Okay? So it's like the in and out is chasing, they are chasing one another. The out is always behind the in. Okay? So out and in is the index number that is pointing to the next slot that is empty, or next slot that is supposed to be retrieved by the user. And here, the same as that, you see the pattern is more or less the same. Here you have to do full up as well. Why? Because if you remove one, that means you got one extra slot for the producer to produce, right? So you have to perform an up. Okay? Is that clear? Okay. Now, this is not done yet because I don't have time. Here I talk about the buffer using the counting semaphore. I hope that you understand why the counting semaphore is used here, right? So the counting semaphore, but I haven't talked about race condition. Yeah? There is race condition that happens here and here, and the count. I don't have, yeah, this not count. I'm going to talk about it next week. We're going to, as you know already, we're going to use the mutual exclusion, either binary semaphore or mutex, to protect this. Because when the producer and the consumer try to update this at the same time, you will have race condition. Okay? So the counting semaphore is to keep track of all this, while the mutual exclusion is basically trying to make sure that the critical section, there's only one thread that is executed. That's the critical section. Okay, I hope you understand, because if I go through that slide, it's a bit more confusing. I know that design is very confusing. I hope you can understand this. If you have questions, you can ask. Google chat or email. To go now, because the lecture is waiting. Okay, I'll see you next week, and some of you I'll see you